Hello everybody. My name is Keshav Vyas. This is
Matthew Varghese.
and
Nathan Marr.
and we will be the sixth team presenting today. And so, as most of the audience has seen, our homework here during the 5-day CNSI Nanoscience program was to create a visual analogy of the concepts that we had learned. And today we'll be discussing, our group was assigned an analogy based on what we did on the 4th day of the camp, which was photolithography. So, let's begin.
So photolithography is a fancy word for patterning, and it's mainly used for small circuits and semiconductors. But we'll get to that a little later. Let's just take a look at the image first. So as you can see, there's a piece of paper. There's a stencil with a design. I'm not sure if it's a cat or like a rabbit or something, but it has a design. And then there's a spray paint. And as you read the image from left to right, you notice that the paper and the stencil continually get smaller and smaller. And also, if you look at the faces on the bottom, for the bigger image, the face loves the image. But then as you keep going down, you notice that the people continually get angrier and angrier. And that's because the actual design that is stenciled onto the paper becomes grainier, so you can't see it as well.
All right, so let's start with the science. So photolithography is made of two words, photo and lithography. Photo basically means light, and lithography is, as what was said earlier, taking one pattern from one surface and transferring it to another. And there are many types of lithography other than photolithography, such as laser lithography and electron beam lithography.
So I'm going to be talking about the 6 main steps that we were studied in regards to photolithography. So essentially what you want when you're doing photolithography is you want to be able to copy a pattern of some sort onto a material that you have. So the specific experiment that we did, we were trying to create like a small circuit board, and we were trying to etch like a pattern onto it, etch a pattern into the copper that was on this circuit board. And the way you'll do it is you'll start off with 3 basic layers. The first one will be a base, or like a little plastic plate in which you'll essentially place everything else on. That's called a substrate. And in this case, in our experiment, we used plastic. On top of that, you'll have a small layer of what you actually want to come up in the design, the actual material. So since we were building a circuit board, we used copper. And on top of that, you'll add a special coating of a chemical called photoresist. And the coating of the photoresist is generally considered like the first step in photolithography. And once you have these like 3-layer sandwich of the substrate, in this case our metal, and then the photoresist, what you want is you'll want to put a mask on it. And a mask is this usually black piece of plastic, or this black piece of plastic with the pattern that you want, and you'll place it on top of this sandwich we have. And essentially what will happen is after you expose this now it's like 4-layer sandwich of substrate, in our case like copper, and then photolith, and then mask to a electromagnetic wave of some kind, it'll essentially change the solubility of the photolith layer on top. And by changing the solubility, you're able to get the pattern that was originally onto that mask onto the photolith. And once you have the pattern on the photolith, your next goal would be to you develop. Taking a step back, after you mask and expose it to the electromagnetic wave, you do something called developing, which will essentially take that difference in solubility that you created by exposing it to the electromagnetic radiation and turn it into the pattern on the photolith. Following that, you do a process called etching, which would be to copy that pattern that's on that photolith onto the copper layer. So now you have a pattern top layer, pattern middle layer, and then you still have your plastic substrate. And after that, you would do something called stripping, in which you would remove the very top layer of the photolith. So in the end, you would be left with this patterned copper layer, or pattern design that you wanted, and then this plastic substrate on which you're building everything off of.
All right, so I'm going to connect that with this image. So the paper serves as the substrate. It's like the base in which we're going to etch the design. And then the stencil is like the mask. So in photolithography, the mask lets in certain parts of the UV light. I mean, the mask covers certain parts of the paper to let UV light in some places and block out UV light in other places. And so in the same way, the stencil covers certain parts of the paper, but then it also exposes certain parts so you can see that design that's in the stencil. And then the actual spray paint can is analogous to the wavelength. So if you look at how the images continually get smaller and how the image also gets grainier, the reason for this is because the wavelength, which in this case is the spray paint can, is still remaining at the same size. So when you're making products at a small level and you're trying to retain that level of quality, you can't use a bigger tool. You need to have smaller tools to retain that quality at a smaller level. And so if you look at the image, the spray paint can still remains the same size throughout the process. And so that's the reason for it becoming grainier.
So actually, since we just established the fact that we interpret the spray can as the wavelength, keeping the wavelength the same as the actual design you want gets smaller will lower the quality. So to increase the quality on a smaller design, you'll use a higher energy, something with a shorter wavelength, such as an X-ray, or maybe even an X-ray is the primary example, but I'm pretty sure you could use gamma rays or anything smaller to create a more detailed design on a smaller scale.
So on that day, we had the privilege of going to a clean room, which lowers the chance of defects appearing on what we're doing photolithography on. And that keeps dust from covering some parts of the mask, or the exposed parts that we don't want to be, or the dust would.
So the dust would, in the clean, basically because we're working with things at such a small scale, it's very easy for little dust particles or very things that are anything on the nanoscale or whatever scale you're building your, whatever scale you're going to do the imprinting on, anything can interfere with that process. So by working in a clean room, you'll be able to minimize such interference and produce more repeatable results and a more, usually more clean end product.
All right, so there are, as with any analogies, limitations to this. So one of the biggest things that we thought was limited was the photoresistant. So in the photolithography process, the photoresistant is used for the patterning process. But in stenciling, you can't really use that because the mask is helping with the process of the actual design. So you can't actually have a photoresistant thing in this example. And so that would also mean that there's a missing process in the development, because without a photoresistant, you can't develop it. And this also means that the very last part, the stripping process, is also missing.
So I think to wrap this up in very short terms, this analogy for us, this analogy is a small part of photolithography in which a mask will be used to differentiate your pattern from what you want, differentiate your pattern from the material you are etching it onto, and in this case, because the wavelength / spray can is the same size, the quality will decrease. To counteract this issue, you can use a higher energy or shorter wavelength electromagnetic wave, and that'll give you a higher image quality for the size. So thank you.
So when you guys were patterning your gold or copper circuits, how did the photoresist interact with the UV light, and is that a positive or negative resist?
So the photoresistant, when the UV light hit the part that was exposed, that became soluble. And the part that was masked, while it's still soluble, it didn't wash away during the development process. So it's a positive photoresist.
All right, I have a question. So this, really like this analogy also because it speaks to a big challenge that a lot of engineers are facing in trying to make transistors that are smaller and smaller, right? That you do come up with these challenges of not being able to make perfect things, because as you get too small, you have challenges like open circuits or holes or whatever it is, that imperfections that can occur. So we're hitting a limit on transistor size, right? So transistors have become smaller and smaller, but there's a limit that we're hitting. Do you guys remember the name of that phenomenon that I'm talking about?
If I'm not mistaken, I think it's Moore's law.
Mm-hmm.
As it held true for a few decades actually, but recently it's slowly becoming to the point where unless there's a major technological breakthrough, Moore's law could be broken. But as of now, it's still pretty strong.
Yeah, we are basically already kind of hitting the plateau. So engineers are coming up with more creative designs in terms of how they geographically, how they orient each of the transistors like within a system. But in terms of the feature size, we are actually kind of already at that limit in terms of how small things can get. Any other questions? Yes? This will be one last question.
Could you just explain the process of the etching? So I understood that the UV light interacts with and makes one of the layers soluble, and that's washed away. Can you just explain what happens after that to the etching on the copper?
Sure. So basically, the etching will just remove the excess copper away it'll remove the excess copper away in the same design that was originally masked on the top layer, and
And also the photoresist protects the copper that's under it, so that's why that copper wouldn't be etched away.
Yeah.
Because that's usually that's like your end result that you that it could be the end result that you want or the part that you want to wash away.
All right. Good job, guys. Thank you.